I do want to get started with today's session as we're running a few minutes late. So I want to hand it over to Dave and Lewis, our co-chairs, to get started with today's topic. So Dave and Lewis, over to you.
Okay, thanks very much, Matt. And this is Dave Stutzman coming to you from southern New Jersey. Nice, bright, sunny day. Hopefully our friends in Florida this week are going to be spared the brunt of the storm and can do better than we had in Houston. So, Lewis?
Hello, hello everyone. I'm coming to you from sunny Nashville, Tennessee. It's actually very pleasant today. It's been cool the last couple of days and low humidity, so we're enjoying the pleasant weather. And it's great to be back with everybody. I'm going to be at the convention this coming week. David is unable to attend, but I would sure like to shake hands personally with any of our audience who turn up there. So look for me. And,
please, they're all friends. Most of them have been on an awful lot of our calls, so hopefully you do meet them.
That's right. We know several of them by face, but it's always good. That's one of the fun things about convention is getting to meet new people and renew relationships with folks that you already know.
Right.
Well, tell us about noise since you're the expert, Brother David.
Well, I will not say that I'm an expert. I will say that the topic is coming up more and more during projects that we're working on, and a lot of it has to do with residential, multifamily, and healthcare projects. We're seeing more and more of an emphasis on noise reduction. Some of it because of regulation, some of it just because it's becoming more into focus on healthcare. For instance, trying to get folks in hospitals a better quality night's sleep. And the architects are taking this to heart and trying to produce designs now that take into at least consideration the sound transmission within the building. So part of the rationale for doing the program today is I've been experiencing some projects where the architects are making selections for interior partitions that they're expecting the partitions to be exceptionally good at noise reduction, but the components that they're using to get there are actually working to the detriment of the sound performance of the partition. And I will get into the detail of that as we get into the presentation, but want to try to explore some of these notions about how to deal with noise and what might be appropriate for noise control in architectural applications. We're not dealing in this presentation with trying to design or trying to give you information about designing sound within a particular room as though it's a concert hall or a theater or something like that. This is more about transmission between rooms. Okay, so we will hopefully get the machine to cooperate. So Lewis, what is noise?
Well, there's a couple of definitions. One of the primary ones in the 21st century in which we're now living is that it is unwanted sound that interferes with communications. But it can also be unwanted sound that interferes with your internal thinking and just normal work. And as David has pointed out, it's becoming people are becoming increasingly conscious of the role that noise has on healthy living, both for people who are trying to recover from illnesses or injuries and for office workers and so forth. So
right.
where does this sound come from?
And I actually have a project currently underway right at the top of the list, adjacent airport. Not only is it an adjacent airport, it's an adjacent military airfield. And literally, the multifamily housing project is in the flight path at the end of the runway. So how do you deal with, think about military aircraft, and when they're taking off, it's not a typical commercial airliner. It's wheels up and they're vertical. So the noise, noise that they're going to experience in that property is going to be tremendous. And the developers right now are scrambling, trying to figure out how to be able to deal with the noise that they're likely to experience on that project.
Speaking of adjacencies, when I was working in Cincinnati, our firm designed Cincinnati's wonderful and exalted Art Deco train station. Was being repurposed to a museum center, but we also, on the back end of it, we built a Omnimax theater, the Omnimax being the 2/3 or 3/4 of a sphere. And the theater was right over a couple of active train lines. And so the challenge was to be able to design this theater so that a fully loaded 3-mile freight train could go underneath it and not disrupt the presentations. And we were, in fact, able to achieve that goal.
The one thing I didn't add to the list, I live in the middle of New Jersey's Pine Barrens, effectively in the middle of the woods. Tree frogs and crickets are actually quite soothing to me for getting a good night's sleep. So, and it all depends upon your perspective, really, because things can, breathing. If you have a spouse and you're in the same bed and you're having a tough time getting to sleep, even breathing can be noise. So how are we actually perceiving noise? And there's really two different kinds that we're typically concerned about in architectural applications. One is airborne noise, the other is structureborne. And the two behave very differently. So airborne is transmitted via air, and it goes through construction, or it can go through construction. The impact noise shown in the bottom is something that is much more difficult to control, because as soon as the noise actually enters the structure, you can see here just from a typical wood frame truss that it can be transmitted any number of ways into adjacent spaces. And trying to control that becomes very, very difficult.
And because the origin of the sound, and which is usually an impact, is directly hitting the something solid, sounds, of course, travel much farther and faster in solids than they do through air, and they're better able to transmit that energy to another vibrating membrane. Whereas airborne sounds, trying to make a wall vibrate, they can do it, but it takes a little more energy.
So one of the things that I've been experiencing here lately, architects are looking at me and saying, well, we have these several different sound sources, and they're actually trying to add the sound levels from two different sources to try to determine what really they need to reduce in an adjacent room. But when it comes to sound, because of the way that the sound waves interact, the 1 + 1 never equals 2, never. So when we have two identical sound sources in volume, we really only get to a 3 decibel increase when we add these two sounds together. When the sound is different enough, you can see when we start adding a 30 and a 40 decibel sound together, the total increase in the sound pressure is actually much smaller. So it's only a 0.4 decibel increase over the 40. So the farther apart they are, the less impact it will have. By the time you get down to a 15 decibel difference, the increase in sound pressure is actually negligible.
What is the noticeable difference in decibels that people typically hear, David?
It's generally considered to be about 5 decibels. So that 5 decibels is noticeable. Below that, you have to really probably almost have an instrument to measure the difference.
So if you're going from 30 to 33, you probably wouldn't even hear it.
Not much. Not much. So how can we, as architects and specifiers, actually try to make a difference in controlling sound? The best way is distance. Inside a building, that might become a little bit problematic. We can't very well pick up a patient room and move it away from everything else causing sound. But with distance, we get probably one of the best ways to control sound, because the sound pressure is inverse to the square of the distance. So you double the distance and you reduce the sound pressure by a factor of 4, which actually makes the rationale when you think about performances, or even when you think about speaking in a large volume room, makes the case for amplification to try to make sure that everything is can be heard and understood, or appreciated in the case of music.
Speaking of music, when my bluegrass band, the Critical Path, was playing some years ago, we had an occasional outdoor venue that was not sound amplified for parties or one thing and another. And my experience is, no matter how hard you play, how much you crank, how hard you hit the instruments, and how loud you sing, the sound's going to go about 10 or 12 feet and it just disappears.
Distance is our friend in helping to control sound.
Yes, but with our band, that was probably a good thing anyway.
No comment on that. Okay. So one of the other things that you can do to help control sound is, put a mass between the source and the receiver. The greater the mass, the greater the absorption of the sound energy, and the less likely of any transmission through that mass.
Well, the harder it is to make it vibrate. It just takes so much more energy to make a concrete wall vibrate as opposed to a drywall partition.
Correct.
And, when we were going over this session, I pointed out to David that my banjos are a lot louder than my guitars or my mandolins. The guitars and mandolins have a wood top that's on the order of 1/10 of an inch thick, but of course a banjo head is a sheet of mylar, and so it doesn't take quite as much energy, and what energy is generated by the strings goes right into making sound. So that's why they are significantly louder than a wooden plucked instrument.
So the barriers is one element that I think we're all probably familiar with. Anybody driving down a highway, you've seen sound barriers put in along residential developments that border the highway. And barriers can actually be pretty effective, especially for outdoor environments. It's not something that we necessarily think of inside of a building, but every partition is a potential barrier. The one that I want to maybe concentrate on today to the greatest extent is absorption. And when it comes to sound, if you don't want to transmit the sound from one room to another, the most effective way to do it is don't allow the sound to leave the room. And if you have plenty of absorption within the room, you can actually reduce the sound pressure and eliminate the transmission or minimize the transmission to adjacent rooms. So absorption at the source is one of the primary ways to control sound. So we were talking about isolation before, especially with impact. And isolation, if you can think of almost building a room within a room that is resiliently isolated from the structure supporting the room. We had one project, it was for ESPN Zone. We were creating a new project in Times Square. And ESPN Zone, if you've been in, you know that they have all kinds of things going on in these places, and one of them is usually a basketball court. This one happened to be on the second floor above another tenant. And the only way that we could make this work is to completely isolate that basketball court from the building structure to make sure that we weren't transmitting any sound into the tenant below. And the last one that we can do with controls is through masking. And this is usually an electronic masking. It's white noise. We're introducing noise into the space essentially to counteract the noise that might be transmitted from an outside source or from another adjacent room into the space. Masking can be really pretty effective, and you can actually control the volume of the masking sound, and that can, in some instances, by raising the volume of the masking sound, be able to reduce the overall transmission into the space or the perception of that transmission. So by additional noise, you reduce the perception of the transmitted noise.
Louise points out that the reason that the sound pressure, the way it's measured in decibels, is not additive is because it's based on a logarithmic scale, and that's so every 10 decibels doubles it, but it's
right. So here's an example of a barrier, typical highway barrier, if you would. So the red circle, the vehicles traveling down the highway, the blue vertical being the barrier between some residential development and the vehicles. What the barrier is effective at is reducing that direct line of sight sound. But what it will not do is eliminate the sound completely, because there's an effect with the diffracted sound, a shadow zone that's created where the residential development is still going to hear the highway, but it's going to be at a diminished volume. The principle that ends up being important here is the height of the barrier in relationship to the direct line of sight sound. So the taller the barrier, the more effective. And in effect, the rule of thumb is that for each meter that barrier is greater than the direct line of sight, it is probably going to reduce the sound pressure by about 1.5 decibels. So you can adjust the height to help control, plus the sound, the distance between the source and the receiver also will help in this kind of an arrangement, trying to use a barrier.
Kevin O'Barron has a comment, David. He says that in addition to noise control for building spaces, noise control of exterior to the building or facility is sometimes a concern. Many of the same principles apply to outdoor noise control as for indoor. Such measures are specified in Division 44, which would be process work for noisy factories.
It can be, absolutely. So you have, for instance, an exterior chiller or an exterior generator trying to service a building, and perhaps you have exterior courtyards where occupants from the building are trying to spend time. You have two different things going on where you don't want to spill noise from your property onto adjacent property, and you want to be able to create an environment where your building occupants can actually enjoy being outside.
I have an idea. Let's put them on the roof.
Well, that gets them up and away from the traffic, and with a little bit of a barrier, probably help.
But Kevin also says that there are warehouses where it applies to warehouses because there are sometimes local noise ordinances, and nothing drives residents nuttier than lots of truck traffic in and out of a warehouse.
That can be a problem.
Milena Palahanska asks, do you place the barrier closer to the source or to the receiver? Oh, good question.
So what do you think? I thought that was a question for you, Louis.
Well, I would think it'd be closer to the receiver, actually. But maybe not. I don't know. I'd never thought of that before. So thank you, Milena, for bringing up the question.
Well, if it's
closer to the source, it doesn't have to be as tall.
Correct. And if you're closer to the source, you're going to eliminate that direct line of sight for a greater distance.
Yeah. Okay.
So
that makes sense.
Yeah, so generally for barriers, you want to get it close to the source because that'll be the most effective way to protect whatever is on the other side.
Dave asked the question, and Dave Metzger asked the question, does the use of barriers effectively increase the noise level within the source area with reflected sounds being added to direct sound?
Back here. Thank you, Dave. Well, it can with the reflected sound because you will get a reflection off of the barrier, and this one is.
But who cares, because you're always driving down the highway with the windows rolled up, the air conditioning going, and you're listening to your favorite bluegrass band on the CD player.
Well, unless there's a residential development on the other side of the highway that's getting the double dose effect of reflected sound.
Kevin also says barrier distance may usually be driven by aesthetics or space constraints, and even things like legal issues like right-of-way and so forth, and where it's practical to build.
Right. I mean, yes, when you're talking about highway construction, right, you have to take into account all the safety issues and the distances from the highway to be able to make sure the highway is still going to be functional. Okay, so wanted to show this illustration about how sound is actually how sound actually works to be transmitted through, in this case, a building wall or partition. So if you have a source at the left-hand side producing the sound, you can get several different forms of that sound. You can have reflected sound in the same room. You can have transmitted sound that would go through the wall. But as you look at the acoustical material, what may not be illustrated all that well, there's some degradation in the sound energy, because as sound hits the acoustic material, that soft fluffy stuff, and even as it hits the wall, some of the sound is transformed into heat energy. So the source sound, the incident sound, if you total the energy with the reflected sound and the transmitted sound, you'll find that the total of the transmitted and reflected is going to be less than the incident sound, because some of it will be lost to heat. Some of it as the sound is absorbed in the acoustic material and as it passes through the partition. So the more that we can absorb on the source side, the less will ever make it to the actual wall, and the less will ever be transmitted into a receiving room. And this is really the key for residential and for healthcare sound control. The things that I'm dealing with almost on a daily basis as to what are we doing for absorption, what are we doing for the wall construction to be able to minimize that sound transmission, and what can we expect to have on the receiving side once we implement all of these sound control measures.
We had one more question about sound barriers. David Adio Moses asks, how effective are trees as sound barriers? In my part of the world, there is a tree called the Leyland cypress that is a bushy, year-round evergreen, and it has a very, very dense foliage, and so people plant them in kind of a staggered row so that they sort of overlap, and they can absorb a fair amount of sound because of the surface area of the leaves and block a certain amount as a barrier, but they have to be very, very thick to do that.
And you have to consider, I don't know that tree, whether or not the foliage actually comes down close to the ground, or whether or not you still have
no, it does.
Line of sight.
It sort of looks, in some ways, looks like a bush. I mean, there are trees that grow to 15, 16, 18 feet tall, but and they're extremely dense. And they have very, like evergreen, not pointy needles like pines, but little needles, not flat leaves as such. Anyway, absorption. Let's talk about absorbing sound, which of those trees it actually can do. The more surface area, that's one of the tricks in acoustic insulation, is that you have you increase the surface area that receives the sound waves to dissipate the sound waves on a larger area.
Yeah, the notion of using porous materials, and this is, it's important to note that it's not just porous as you think of it perhaps for passing liquid through the material, but it's acoustically porous materials. And what might be seemingly porous for liquid may not be necessarily porous for acoustic. So we're looking for that soft, fluffy stuff. We had a recent project for a casino. It was a convention center, and they had operable panel partitions. So it was I think it was about 150,000 square foot convention center, and we had a call sometime after the facility was completed, and the architect started talking to me about the acoustics and the performance of the partitions and the operable partitions themselves. It took some discussion until I finally realized that what the issue was they had configured the operable partitions to create a relatively small room within the convention center, and whomever had rented the space was complaining about the acoustics within the room because the panel partitions were specified with vinyl wall covering and often used material for the surface finish, but because they condensed the space, the reverberation within the room was so great that the meeting space was really unusable. The the discussion or the conference that was going on was unintelligible because of the reverberation. So the panels really had no absorptive capacity. The only absorption was ceiling and the carpet on the floor. And because they changed the volume of the space, those porous materials were not nearly enough to help control the absorption or help control the reflection and the reverberation within the space. So it's important to understand all the surfaces in a space, floor, ceiling, and walls, and in this case, changeable walls that can change the volume and change the performance of the acoustics within the space. But when you start looking at absorptive materials and you're putting it on a solid substrate, the distance that porous material is standing off of the substrate actually also makes a difference in the absorption capacity. So if you give yourself some space, now you can use all 6 surfaces of the absorber to be able to help in controlling the sound instead of only the face.
Thomas Pratt asks, how big were those casino rooms?
I don't know the size when they actually configured it where it was a problem. I can imagine that it was still probably several hundred square feet, maybe even 1,000 square feet. You know, you consider that the whole convention center was about 150,000. You know, I can't imagine that it got it down to down to 100 square feet. You know, because it'd only be a couple panels on each side, but at least it was small enough to make a big difference.
Okay, and what is a cavity resonator other than the space inside my mandolin?
I thought it was a loose dental filling. No, actually, cavity resonator. It's a concept. It's sort of a strange term in acoustics. Anybody doing K to 12, especially high school, I suppose, facilities, gymnasiums, might be familiar with a product that's, I think, called Sound Blocks, where it was a CMU. It has a slit in the face of the CMU to actually allow sound into the core of the CMU. And the idea is that with that slit, you're allowing the sound in. The sound is going to bounce around inside the CMU and actually degrade to a point where, because it's resonating, the CMU is actually resonating and absorbing the sound, that it is helping to control the sound within the gymnasium.
In effect, you're increasing the wall area by a factor of 3 or 4 then.
Right, but you're giving this cavity inside the block the capacity to be able to resonate and to be able to absorb that sound. A simple gypboard partition actually performs the same thing, or can, because you're creating that internal cavity and allowing both faces to resonate to some degree. The one that we didn't touch on is the panel absorbers. These can actually be solid panels. It could be a plywood. It could be dimensional lumber. But spaced from a backing now and being able to be somewhat resiliently mounted, it can also absorb energy. And you see this kind of a thing used in theaters and concert halls often, where the perimeter walls may have wood panels, but they're there as potential absorbers, being able to resonate themselves within the space and absorb the sound that way. So, Louis, are you going to perform today in your falsetto voice, or are you going to perform today in that really deep bass voice.
What deep bass voice. Yes, I don't know if the folks are up to hearing me yodel or not.
I think we can.
We were talking about this the other night, and I had a friend who's active in a Civil War enactment group who plays the fife, and rather than carrying a rifle. And he says on a clear day, you can hear his fife 2 miles away. And that's one of the reasons why they use them in the Army, is because the sound, being so high pitched, would cut through the lower sounds, lower frequency sounds, and you could hear it over the rifles being shot, over cannon, over almost anything. It would still be audible.
And they were using the fifes as communication signals
Yes.
for troop movement.
Yes, exactly.
So, and the frequency does matter, because low frequencies do have to be significantly louder to be perceived to be the same loudness. And this is what Lewis is just explaining. The fife doesn't need to be nearly as loud, but penetrates and is perceived as being much louder over the lower frequency sounds. So if we understand what the frequency range is of our sound source, we can actually use that to an advantage in selecting materials and selecting assemblies to be able to reduce what is really considered to be the noise.
We were talking, David and I were talking the other night about that in the Middle Ages, when you had church buildings, I should say, that were all stone and hard surfaces, that the buildings, depending upon the size and the configuration of the spaces, would have a natural frequency, a resonant frequency, and the priests who were administering could learn to talk at that resonant frequency, and then the choir would use that resonant frequency as the tonic note for the Gregorian chants, or plain song as it's sometimes known, because the building itself would act as a natural amplifier for those particular frequencies.
So the one thing that we see architects and the building industry in general relying on today for noise control, especially for partitions, is the STC rating. And we need to be able to make sure that we understand what STC rating means. So STC, sound transmission control coefficient, is a single number that represents an average loss, but that average is compared to a standard contour, and the STC rating is the position of that standard contour at 500 hertz. So realizing that we're picking a single frequency from a standard contour, that we can have performance above and below that standard contour. And depending upon what frequencies we have and the position within in relation to the contour, it could make a significant difference. So we could pick an STC rating for a particular partition, not understanding what the frequency response is, and we could be producing a worse result by picking a higher STC assembly.
Have a couple of comments to get caught up on, David.
Sure.
Kevin corrected my statement. The fifes were not used for communicating. They were for marching and stuff. Actually, the bugles and drums were used for controlling movement of groups within battles. And Kevin is quite right on that. I misspoke. And then Charles Bennett says, I have been told recently that OITC, outside-inside transmission coefficient, is more applicable these days than STC.
Only as it relates to exterior noise being transmitted to building interiors. So going back to the multifamily residential next to the airfield, yes, OITC is the one that you would need to be concerned about there. The measurement is nearly the same.
Especially for windows.
Yes.
Fenestration.
Okay. So here is an example of two different STC ratings. The heavy black line is the standard contour that's used to measure STC. And the dot that you see on both heavy black lines is the STC rating, because that's where the contour crosses the 500 hertz frequency. So what's happening is, if you look at the one on the left, the frequency response, the dashed line of that particular partition, is seemingly much closer to the standard contour, and is actually significantly less than the example on the right, especially at the lower frequencies. Yet the example on the right shows a much lower STC rating. So what's important to understand is, to establish STC, the frequency response must meet two conditions. So at each of the 16 frequencies between 125 and 4,000 hertz, they'll look at the deficiencies, the distance below the standard curve at each frequency. The sum of those deficiencies must be less than 32. So you could have an average of 2 decibel deficiency below the standard curve across all 16 frequencies. The other condition that you must meet is a single deficiency must be less than 8. So the example on the right, if you look at the deficiency at 2000 hertz, that is 8. So that frequency alone is controlling the determination of the STC and is dragging the curve downward. On the left, you have very few deficiency, or you have many deficiencies, but small quantity or small difference below the curve. And we're looking then at the total being less than 32 for each one of the 16 frequencies. So that one is pushing the STC higher. But if you're looking for very good performance at low frequency, say you have a sleeping room next to a mechanical room, and for mechanical room, because of the rotating equipment, lower frequency is much more important to control because that's where all the noise is. Perhaps the STC 38 on the right is a better choice because it has better performance at the lower frequencies. So STC can be misleading. Remember, it's a single number representing performance across the full range of 16 frequencies that we're measuring for human perception. And it's important to understand where each one of these assemblies that we're using, what their performance is at these specific frequencies, as well as an overall STC average rating. So how can we make things better? Lewis, are you going to lead us through this? What are the number one choices?
No, well, the number one choice is to seal all the openings.
Yes.
Because even an amazing amount of sound, amazing amount of noise can go through even a 1/4 inch opening. So that's one of the things. But obviously there are certain things that you can do. We can increase the weight, we increase the mass, so the more of the sound is transmitted into, it takes more of that energy out of the sound, out of the noise, to make the mass vibrate. So that helps.
Okay, and this next one, the next one is my favorite, and this is one where it's been complicated by some of the firms that we're working with. The Gypsum Association publishes their GA 600, their fire resistance directory, and in the fire resistance directory, they list many assemblies, and most of those assemblies are also listed with an STC rating. What's happened is I have architectural firms selecting assemblies from the Gypsum Association and expecting that the assemblies that they're using for their particular project are going to meet the same STC rating. What they fail to remember is the Gypsum Association ratings are based upon 18 mil studs, 25 gauge, at 24 centers. And when we're talking about most of the commercial construction that we're involved with, I will have one architect that insists that he's going to use the heaviest stud available, a 33 mil stud, 20 gauge, and put it at 12 inch or 16 inch centers. We cannot get the same acoustic performance. It's impossible to get the same acoustic performance as is showing in the Gypsum Association book. And yet they're relying on the book to show the STC ratings and expecting that that's the kind of result that they're going to get. Probably the best result we're going to get, eliminate the studs completely and make the two faces of the partition independent so that there's no direct connection. So there's,
isn't that in your next slide?
Oh, it's right here, number 3.
Oh, okay, yes.
Right? Just eliminate the studs.
If you can do that, yes.
Yeah, if that were to be possible. So have two completely independent faces for the partition, no ties between them, so you're not directly transmitting, you're trying to rely on that cavity to be able to minimize the transmission from one side to the other.
Yeah, there we are with the staggered studs. And even though they may be sitting on a common track and have a common track at the top, it will still work because we're not connecting those two vibrating diaphragms.
Right, and probably the worst thing that you can do, if you spend the money, you do the double studs, you separate them, and think about a hospital condition where you have patient rooms back-to-back head walls, back-to-back penetrations because of the head walls, and they're probably in the same stud cavity. If those can't be separated, you've probably just defeated an awful lot of what you've accomplished by providing separate studs for each face. We talked about the increased mass, but one of the ways that can go a long way to helping is have two different faces with different weights, because the resonant frequency of each face then is different and less likely to transmit sound because of the difference in the frequencies. So we get down to the end. Resilient attachments, resilient clips to attach one face And we only need one face to be resiliently attached, something to help allow that face to act as a resonator itself to help dissipate the sound. We can try to separate the two faces as much as we possibly can, and that's going to be limited certainly by the space constraints within a building, because you can't lose everything to partition dimensions. We still need to be able to use the spaces. We can add isolation blankets, and it's not always necessary to fill the space completely. We just need to be able to have enough absorption inside that space to be able to reduce the sound effectively through the partition. And Lewis mentioned perimeter caulking. So how important is that perimeter caulking? I don't know. Let's take a look. Lewis, what do you think? Is it important?
When David showed this to me the other night, I was absolutely amazed. I had no idea it was made that much difference in the sound transmission. But
yeah, so it doesn't seem like a really big deal, and it seems like a relatively simple solution. But gosh, if we pay attention to the perimeter, to the openings through the partition as well, if we can seal those and minimize the air path, the direct air path through the partitions, we've done probably more than anything else is possible to reduce the sound transmission.
We had a couple of comments on the previous illustration of the resilient attachment. Elias asked, was the furring shown upside down? I really don't think it makes any difference which direction it's pointing. But Philippe Moquin says, instead of showing it between gypsum layers, they have been having very good success with mounting the resilient furring directly to the studs and then attaching the gypboard layers to the resilient furring.
Yeah, either way will work. And yeah, it doesn't really matter the direction that you're mounting the resilient channel. And there are all kinds of resilient channels, clips, and all kinds of devices you can use. One of the biggest difficulties in the resilient channel, or sometimes in hat channels, thinking that they're resilient channel, you need to make sure that you're only attaching one flange, because you can see here the second flange is missing, allowing it to vibrate.
Yeah, and well, what it does is it's instead of passing the vibrations through, it's focusing the vibrations on that outer face and changing the sound energy into mechanical energy to try to vibrate that piece of chipboard like a membrane.
Correct.
A sounding board. Let's see. Oh, we had another comment from Milena Palahanska. Another issue to share, we do as much as preventative noise approaches with the walls and floor ceiling, but when the architect does not provide soundproof door or with gap on the bottom of all or with too big a gap at the bottom, all the work on the walls is meaningless.
Yes, any opening through the wall, whether it's door, window, observation window. I think about hotels. Yeah, hotels especially. How many of you been in a hotel room recently? You wake up in the morning and there's your invoice sitting on the floor just inside the door. The only way that they can do that is without a door bottom. As soon as you put an acoustic door bottom to contact the threshold, they can no longer get that through. And actually, sometimes that's a conscious decision on the part of the hotel, because they want to be able to leave that invoice for you.
We have a comment from Ken Hersenberg, who is widely respected for his wonderful contributions to the Four Specs forum. with lots of good advice. He says, I would suggest a mock-up when using resilient channels, as many installers don't know how to properly install them, fastening through that transport sound. For the sealant shot, would you be addressing flanking paths? So well, there's two comments in there. Yes, all of these things. When one of my previous employers did a lot of hotels, and very large hotels, 1,500 room hotels, and we would have a mock-up guest room, and it would closely observe the construction of putting the insulation in the walls, one thing and another. And then we would actually test the walls to make sure that they were working appropriately. And sometimes we had to go back and change some of the construction techniques to be able to achieve the level of quiet that we wanted.
Yeah, and a field sound test is not really all that expensive of a test to perform. And the only thing that you need to be aware is you're probably not going to get the laboratory results. You're going to get something less than what you might find in the Gypsum Association manual.
Okay. Well, we have one last one comment from Dave Metzger, and we really need to make that about the last one that we can, because we're running out of time. He says these drawings all show the stud track not in contact with the substrate, what's supporting it. And obviously the runner track has to be fastened to the substrate, but with a 3/8 inch or so gap between the edge of the gypboard and the substrate to allow a sealant installation. The face of the runner then acts as a stop or backup for the sealant. But, and of course, many people will install you can get a gasket to go under the sill track, as pointed out by Dwayne Epp, that that makes up for some of the ups and downs of the floor slab, and also gives you a certain level of resilience and closing, making sure that space is closed off very well, right, even though it's not multiple layers of sealant.
Right. It's only a matter of just trying to make sure we close those gaps. And if we put a bead of sealant under the stud track and fasten the track down to the slab, we've probably closed that gap. And then it's a matter of sealing the gypsum faces.
My mother invented a word, coined the word gaposis, to refer to something where there was a gap where it should have been filled in. So I offer that freely to this august assemblage today. And one parting thing, we did talk about frequencies, and I want you to know that the local Circle Freeway here in Nashville is I-440, but is often known as A-440.
Okay.
So what have you decided for us to talk about in October, David?
That's to be determined, and it might be dependent upon what you come back from Construct with. But I did want to finish up and at least give a thank you to Leslie Doell. His acoustics book has been one of the companions that I refer to regularly. It's an excellently written book. It's an older book, but it's extremely helpful. And his book was the source for most of the illustrations today.
All right. Well, thanks everyone for spending your very valuable time with us, and keep those cards and letters coming in, friends and neighbors, so with ideas about what you would like to have David and I talk with you about, because we really view this as your program, not ours, and so we want to hear from you.
All right. Look forward to seeing you next month, October 5th, the first Thursday, 3 o'clock Eastern. Thanks for joining us.